So my talk is titled as Modern Streaming Data Systems. So I will be mostly discussing about my experience with the system, and especially when I started working on this project called AIR at University of Luxembourg. So it was a part of my PhD postdoc research, and I will be discussing mostly some fundamentals about streaming data systems. This is the overview. And then we will slowly move on to the design aspect. How did we design a system which is meant for large-scale stream data processing? And finally, we'll look at the experiments which I've done and some conclusions and some future directions. So, so if you look at data systems, right, in general, not even streaming data systems, you can think of something like which takes all the data and then process something, apply some function on top of it. So that's the function of a data system, right, in general. So the function, we can call it as a query. And you can think a data system in this, generic formula. But then when it comes to streaming data systems, this is again a data system which is designed with infinite data in mind. So we'll see what are these infinite data, but the formula would remain the same. If we are performing a query, it can be any sort of query, which is performed on top of that infinite data. So talking about the infinite data, it can be in the form of streams, right? When we talk about streams, it comes generally with a timestamp. So it can be some transaction-related data, and we are supposed to do some analytics on the data. It can be some fraud detection on bank transactions, and also it can be some data which is coming from different IoT sensors also. And our streaming data systems, or SDS, is supposed to perform some operations like anomaly detection or some alarm generation sort of thing. And also it can be the other application where you get stream of tweets or some comments which you're getting from social media sort of thing. We are supposed to process it, classify it, So it's a duty of all the streaming data system to perform the operation which is shown in the left-hand side of the screen. And it can be also some other data set, something like a dynamic graph stream. And if it is a graph, we are supposed to perform some graph-based analytics, performing some shortest path algorithm or something on top of. And also it can be images, right? It can be, if we look at the recent trend, it can be images from Chandrayaan rover or something. So our system is supposed to process it, classify it, perform some analytics. So as a stream data system engineer, nothing matters, whether it's an image or graph or process it. So we should have that perspective in the mind. And going something deeper into the streaming system itself. Historically speaking, the streaming systems are meant to give low latency. It should be low latency, and that kind of abstracting it. It's low latency, inaccurate, and speculative results. So that's what we really expect from a streaming data systems. If we talk about something beyond or before 2013 or so, that's the expectation from the system, right? Inaccurate, low latency, and speculative results. Those all are expected from a streaming system. So often we use this stream data processing system along with a more capable batch system. So this person, his name is Nathan Mars. He's from Twitter. He's working as an engineer, streaming data engineer there. So he has introduced this architecture called Lambda architecture, which exactly says the same. The streaming data system is expected to give low latency result, but then on parallel to that, we should also have a batch data processing system, which will give you correct results, but with some latency. Right? We have to bear that. So if you want to work on some real-time analytics that we saw before, we should have these kind of pipeline, where you should have a streaming layer or real-time layer, which is nothing but the stream path, and also a batch processing layer in parallel. So that's one thing which had been using, people have been using in many companies for long, for real-time analytics. And here you can see that the stream right, with set of events coming into the system, and it's been divided or replicated into two different pipelines. And in the case of batch data processing system, we have to wait until you create a batch. Then only you can actually process it, right? That's the problem with the batch engine. You should have data in your hand so that you can process over it, which will generate a set of processes. And those processes will get terminated once you are done with the batch processing, right? So can somebody tell an example of a batch system? Can be anything, right? It can be our database management system. Yeah. Yeah. Correct. So yeah, in terms of system, data processing system, you can also think in terms of Hadoop or similar system, where you're assuming that you have the data with you before you start processing it, right? So that's the assumption, even database, right? So you should have the data before you start performing a query on it, right? So those kind of system is a batch system. And here we are actually trying to do real-time analytics on stream using batch system. But the problem that you see is that you have to wait until you get the batch, whatever the size of the batch, and then you apply your query on top of it and get the results. And if you look at the the state-of-the-art stream batch data processing system, it still has some delay until you have to wait until you get the data, process it. It will take maybe an hour to perform that task over it, right? So by that time, you'll have a lot of other data to process, which is kind of blocked, right, or has to be buffered. So this interesting architecture, Lambda architecture, would help you to process these streams in parallel, the rest of the streams, so that one by one, it can take the data and still give some, analytical output, right? But over the period of time, the batch would catch up. You'll consider again this replicated data in the form of batch, and you will tend to give out accurate results. So it's sort of giving you an eventual consistency-based system, right? You're getting stream. I mean, since we have this low latency results, since we wanted to have that, we can use a streaming system in parallel. That would be beneficial to see some random outputs, right? But all the time, it will be replaced by the results that you're getting from the batch layer. So, yeah.
By the time the batch system catches up, at that time you might already have taken some decisions based upon streaming of the
maybe, yeah.
that they have gone irreversibly wrong.
Those has to be handled. Maybe repair write sort of protocol has to be issued in that case. But we are generally talking about real-time analytics. Maybe if it is generating a histogram sort of thing, based on current trends, which does not really have any catastrophic effect on the society or anything. It's just analytics, right? Real-time analytics. But of course, like you mentioned, for cases where accuracy is important, we should not really go with some inaccurate methods like these. But if low latency is there, and if it is just an analytics, we can still go with this approach, right?
It depends on in some cases, I could say, yeah, waiting for the next data of the back and possibly be better.
Correct.
In other cases, it's possible that if you wait for a batch to get aggregated,
yeah,
the answer you get is already
obsolete. Yeah, that can happen with the batch. If you just have only one pipeline, and it will take like
the one who rely on.
No, here in this case, we take both, right? We have both the pipelines together running, and the first pipeline would give you more accurate results, and the second pipeline will give you real-time but low accuracy results, and which means that the recent output cannot be fully trusted. But over the time, yeah.
Why you say that?
Yeah. So let's
Depends on. Now that's outside of the scope of the script. What can we do better? Instead of waiting for the full batch, can we do better in different pieces and eventually catch up to the activity? They're not out there to see whether data that they can be as good as the batch. They're not questioning whether the batch is. We are happy they are able to ask when are we able to batch. That's very critical.
So let's say that if you want to
But then considering this is not take a lot of time. 8 per hour. Let's say can do some minimize the impact.
again, you can connect that with the windows, right? How long you need to wait. Let's say 10-second window. So if you're getting the entire data, so you can perform whatever your computation you want to do, right? You will get the accurate result, right? Maybe let's say if you're booking something online, right? Let's say some bus ticket or train ticket, it has a window for 1 day, right? So if you wait for 1 day, you will tend to get the correct results, right, at the end. So you wait for the entire day to finish and then execute. But here you can say that the system would take when somebody is making a registration, that would go into the streaming system and increases the count. So over the day, you will get multiple results. At the end, you will get the correct answer. So eventually, you will slowly moving to the consistent state. Yeah, you can also think in that way. It's coming into the system. We are applying the same operations or algorithm, whatever it is, and giving out the results, right, for the small data. But you are not considering the entire data, right? You have a question? Yeah. Correct. Yeah. Yeah. Yeah, again, I can relate. Yeah. Yeah, probably. Correct. You can relate. I mean, it's a bit complicated example, but you're saying that we can wait until, if it is 1 day or something, you can wait until the end of the day to get to know the actual score, right?
The third and final is getting from 4 different streams.
Yeah.
That particular information.
Yeah.
And then is computing whether the batsman is out or not.
Correct.
The wicketkeeper is immediately telling them.
Yeah, so more like that. If you wait for some time, you will get the correct answer, right? Because you have the entire data from all the directions or dimensions to decide that. So that's what is happening. So generally, these systems are not designed to give correct answers, right, with respect to window or So and there's nothing wrong in that, but there are some drawbacks associated with this Lambda architecture. So we have to maintain 2 different tech stacks, 2 different teams who are maintaining this pipeline and operational effort. This is something which is very important. So people started thinking more of why can we design a unified system which can provide low latency at the same time accuracy, right? So it should be real time. So we wanted to avoid this batch layer. We want to make stream more accurate, but at the same time low latency. So how do we do that? So that's the effort. So yeah, so like I said, inaccuracy of the streaming system can be due to the use of approximation algorithms, right? So we wanted to run not a complete algorithm on the data. So we wanted to get quick results, right? So we generally stick with such algorithms. And also it's not designed to ensure correctness. So people take advantage of that aspect. So we don't need to wait until you get the entire data. So that is one thing which we have to break in this convention. So I hope you understood why do we really need a new system or a unified system for stream data processing. Right? So you stick on this point and just move ahead. So yeah, something more about the fundamental stream data processing system. So the kind of operations that we do inside this SDS or stream data processing system could be classified into different types. And the first classification is time agnostic. Time is not dependent on time. Such operations, for instance, filter operations. You get a stream of data, so you apply an operation on an event or a condition, check for a condition, and if it satisfies the condition, you give out the result. Time agnostic. There's nothing blocking you from restricting a particular event to go beyond that filter. If it satisfies the condition, it can go to the next level, right? Checking for a condition. For example, if you are dealing with some web analytics sort of application, there are different ways, right? The people will approach a website or something. You can click on it, or you can subscribe or do some product, or you can purchase something. Yeah? So these are different classes, right, of a particular event. So based on your use case, you can approach, you can put a filter condition. You're interested only in the click events, right? So you can apply a filter condition, and there's nothing kind of blocking you from releasing the result here. It's not dependent on time. Yeah. Yeah, so if it is time invariant, it will fall into this category, right? Yeah. We will see. Yeah. So there is one more example, inner join, right? Suppose you are getting two stream of data, right? You can assume that two tables are coming into our system. You can perform an inner join. If the one component of table has a matching element in the other table, you can actually release the result. Right? So in some sense, you can also treat inner join also as a time agnostic operation. And also some approximation algorithm where we don't care much about the completeness of the data, but it gathers some data, apply some algorithm, give out the result. For example, if it is a graph database or something, we'll apply some algorithm on it, right? And to find out the shortest path between two nodes or something. And then we'll release the result. We don't care whether you got the entire data with us, right? So application of approximate algorithm is also more like a time agnostic operation. And then comes windowing. So this is another interesting operation where initially we had this definition, streaming data definition. It's like a query we apply on the entire infinite data. So now that's practically not possible. So people came up with this notion of windowing, where you are interested in only a segment of the data, not the entire data, right? So there are different types of windows, fixed windows. It will, based on the time, we can divide or chop the stream into fixed windows, non-overlapping windows, and it can be also sliding, right? So there is some level of intersection. And also it can be sessions. Session windows can be overlapping and non-overlapping, or it can vary in sizes. So we'll see more about this, but in general, these windows, yeah, come into picture. You have a question? Yeah. I'm sorry, what? So this is more, you can treat it more like an analytical data stream at the moment. The transaction is something different, right? Yeah, of course, we can come up with a method for doing transactional kind of analytics on the streams, but right now you can stick with analytical processing rather than transactional. Yeah, read operations. Yeah. So now the question is whether there is two notion of time here when you talk about streaming data system. The one is the processing time, other is the event time. The name implies event time is the time which is implanted onto an event by the source, right? For example, if it is a sensor, the sensor is generating the event, and the time which is followed by the event will be implanted on the message, right? So that's the event time. And the processing time is the time which is followed by the streaming data system, right? So that are the two different types of time we need to consider, and based on which we can consider two variants of windowing. Processing window based on windowing based on processing time, and windowing based on event time. So let's look at the processing-based window, processing time-based window, so which can be treated as something like this. The data is coming into our system, and the system is following a processing time, right? The wall clock time followed by the system. And here we know the completeness of the data, right? It will wait for 10 seconds. Suppose you are asked to perform a query over a 10-second data. So you know the completeness of the query, right? You will start from 0 and then wait till 9 seconds. You say that it's a 10-second window, and you're damn sure about the completeness. You have the entire data, right? But yeah, so that's the processing time window, right? Processing time based window. But the downside here is that if the event time, which is carried by the events, these kind of events, and the processing time are different, it can create some issues, right? Just think about, some events which are generated from all your mobile phones, right? So if you're using an Apple or Android phone, they tend to release some usage statistics, right, in real time onto the Apple server, right, or the service provider server. And they have some statistics. They will process this data and perform some real-time analytics and make a study on this data. Right? So suppose you are turning off your phone, or you are putting in air flight mode, or if you are catching an air flight for a large duration, the system or the application will continue to generate, but it is buffered within the system, right? The events, which means that once you are connecting back to the network, all this message will get released, which means that the message they are getting here are being delayed for 12 hours, but it's still been falling into a recent window. So that can create a spike, right? But it is analytically incorrect, right? You're getting a spike for no reason. Right? So the cases where the event time is far behind processing time, this kind of processing time can create incorrectness in the output or whatever. Right? So that's why it's the global standard we are supposed to follow is event time based window and not the processing time based window, which means that we should not look at the wall clock. The system should not look at the wall clock or the timing followed by the distributed or streaming data processing system for performing this kind of windowed operation, but instead it should look into the event and the time associated with this event for deciding this logical window, right? So that's important. So prior to 2016, that was not addressed, and in most of the recent modern systems, it's been addressed to a large extent. So now the things are slightly different. So now in the processing time, you're getting the data. So within the stream data processing system, you have to maintain different buckets with respect to the event time. And once you get the data, you will examine the time and relate that to the corresponding buckets. Right? So that's what we have to do. But then there is a question of when can we release this window? Suppose you have enough data here in this particular window, in this particular timeline. So how do you know that you got the entire data so that you can release the result? Right? So there should be a notion of time which is beyond the processing time, right? Which gives you an idea that at least till this point, you got all the data, and now you can pass or you can perform your query and release the result to the next downstream activities. So that is very important in terms of stream data processing system. Yeah. Yeah, each event is generated by a sensor or some source, right? So it is coming with a timestamp of that source. That's the event time, right? So we have to now look into that event time. The SDS, the streaming data system, has to look at this SDS and decide the time. Correct. Yeah. So that's the big issue here. So how do we know that we got the entire data so that you can apply your query and release the result to the next downstream? It can be anything, right? So by static, you mean fixed windows, right? It can be fixed windows because The streaming data system should support all these windowing semantics, fixer, sliding, or sessions, and everything. So now this model that we adopted would easily work for sessions, right? So you just need to look at the window and create the sessions and give out the results. But we have to make sure, to guarantee the correctness, which we are aiming for, right? Low latency and correctness. For guaranteeing the correctness, we have to have a correct notion of timing, and which gives an insight into till that point we have received all the data, right? So how do you do that? Okay. They should be, yeah. They should be. Yeah. Even the process, when I say processing time or overclock time, it is assumed to be synchronized in millisecond range or whatever. So, but yeah, if you are following the event time, again, that time has to be informed to all the nodes or processors within the system. Yeah. Yeah. So yeah, so in my research, I was focusing on building something known as data flow processing engine for streams. So let's see why that is important. So this is a big picture, and we were aiming at designing, like I said, data flow processing engine that gives something known as high sustainable throughput. The word high sustainable throughput has something to do with low latency. That's what we wanted, and also throughput. So we'll see why that is important. So far we have looked at stream data processing, or SDS. It's here. We're getting a stream of data, unbounded set of events, and it's also kind of giving out results in the form of streams. After processing a window, we're giving out an event with a timestamp, right, of that window. And events, we know, right? It's a key value pair sort of thing. With a value, can be image or tuple or anything, and a timestamp. And there is something known as throughput, which we already looked at. It is nothing but the number of events per second. So when it comes to input throughput, we could say that the number of throughput the system has ingested per second. For instance, if I'm running this stream data processing system for 10 seconds, right? And if I had intaken, let's say, 10 million events, so you can easily calculate an average throughput, right? 1 million. So 10,000 million divided by 10 seconds, that will give you 1 second intake, which is nothing but the input throughput of the system. And there are different operations that we perform inside the system. And it can be time agnostic, like map, filter, split, etc. It also can be windowed operation, which is related to the time, or we can call it as stateful operators in some sense. So the former would be more stateless, and the second one would be more stateful operators. And sometimes for your problem, you may need a combination of all these: map, filter, join, and finally a windowed event or set of other time agnostic processes, and then finally a windowed operation. It can be quite complex, right? Depending upon what you really want to do, right? We can define a sequence of such operations. Sometimes you apply filter, sometimes you apply split, right? Sometimes you want to do join with some other data, and finally you want to do a grouping based on window, right? So all this come into picture. So this is nothing but the data flow, right? So that's where the importance of data flow processing engine comes into picture. Yeah, we slightly going back to the same setting where you have multiple streams here. The first one is fixed window, right? As the name indicates, no overlapping segments. They are non-overlapping segments divided based on the temporal aspects. And then it can be overlapping, right? This is overlapping window, or it can be sessions. Segments can overlap and also vary in the sizes. So then there are many abstractions that are possible on top of these streams. And the only thing is that it has to be defined for a window. For instance, you can also think as having an SQL layer over it, but SQL layer should be associated with a window. Right? This shows that you're performing, the data is having some set of tables which are coming in, right, from the table stream, and then you are applying some filter condition and doing a grouping, but everything with respect to a window. So it's called continuous queries rather than a simple SQL query, right? Since it is associated with the time, we have to iteratively perform this query over all this data, right? So yeah, So, and we know that, if you have a background in database, we know that this query could be expressed in terms of query plans, right? That's how it's been processed. So given a query, it will be converted into a query plan. There can be multiple query plans possible, and the optimizer would choose the best, right? And this query plan, if you look, could be also interpreted in the form of a DAG. Which means that if you have a data flow processing engine, we can easily build a system which can process SQL or any other abstractions, right? So we were interested in building a data flow processing engine which can take a data flows input and can process over the data stream or data. Okay? So yeah, let's look at what is high sustainable throughput. So as per the definition, you can see that it's a maximum throughput the system can ingest without showing something called back pressure. It is nothing but increased in the latency without showing increased in the latency. So let's look at a scenario here. So it's an experiment which I performed in my lab where I have installed Apache Spark, which is a stream data processing system, over 2 nodes. And so it's meant to do a Yahoo streaming benchmark. The Yahoo streaming benchmark is nothing but the sequence of operations, right? So it's been observed that when you try to increase the throughput, right, the table depicts the same thing. When you try to increase the throughput, we get a latency, the time required for processing that query. Yeah, yeah. Hmm.
What is the big difference like table or select versus the big?
Oh, for the table as well as window, right?
You are saying that.
Yeah. So yeah, let's assume that you got a data, for a batch data, which means that you waited for a day and got the data. You loaded that into a database and performed that query, and we know that it contains the data for that particular window, 1 day window, and you perform the query, you get the results. It's exactly the same, right? So you have the data which is coming into your system. Sometimes it get mixed up. Multiple windows will get mixed up in the stream, and you have to the system has to figure out which all data would fall under which window, and on that window you perform the query, and it's exactly the same, right? It's just like having taken a batch, divide into different time duration with respect to the query, and performing independent query on that. It's just the same. Right? So that's why we can say that if you have a stream data processing system, you can implement a relational database management system or some query processing engine using this kind of system. So it's a generic class in that sense, streaming data system. So if you just remove the time aspect, it will become a batch processing engine. So yeah. So back to the maximum high sustainable throughput. It's the highest throughput the system can ingest without showing prolonged increase in the latency. So let's try to give, in our experiment, we try to increase the throughput from, let's say, 1 million to 5 million, 12.5. You can see that there is a variation in the latency from less than 1 second and then to 5 seconds or so. So then from a particular point onwards, it's kind of going very high. It's going into the roof, right? So we can say that 12.5 can be treated as the sustainable throughput of this system in this configuration for this particular application, right? So how it also gives a notion of how well we are utilizing, how well the system that we develop is utilizing the resources in terms of throughput and latency. So for Spark, we can say that 12.5 million would be the highest sustainable throughput. Yeah, so there is a phenomenon which would happen when you try to give more data into the system, right? Especially due to the overflow of the buffers within the system. So when you try to give more throughput, so we'll see that it will reflect on the latency. Yeah. So yeah, if you go to 13, from 12.5 to 13, there's a significant jump, right? So generally, when you say, a system is real time, it's also a bit subjective. You'll say that if it is a 5-second duration or something, and if it is going beyond that, it's not treated as a real time machine. So here we just go by that definition. Let's say if it is going much higher than that particular number, it's not acting in real time. But we'll also see this observation that it's going too high beyond that number. Not as such. So it's a slightly vague term. Usually happens in this kind of system when you try to give more data into the system. Especially people say that it's because of the memory overflow. The system is not able to handle more data, right? And yeah, so this is one way you can observe the back pressure. So if you go with
Vinu, so isn't the earlier slide? So isn't this the normal the basic queuing theory problem? I mean, you have a server and there is a queue of things coming in.
Yeah.
So and depending on the processing speed of the server and the rate at which
correct
things are flowing in, you can predict the average output throughput, and you can also figure out whether the queue that will build up behind the server,
correct,
will that grow sort of ad infinitum?
Yeah. So
like if the server is too slow,
correct, yeah,
then the queue will just keep on piling up.
Yeah.
And this is a basic queuing theory problem.
Yeah.
Right? So is it the same thing as that, or is
it's the same? Yeah, but then you can also see that it's a distributed system where there are too many processes running, right? Like I mentioned, if you have a data flow, each of these operators in the data flow will be replicated n times, which means that they have to receive and send messages, which means that and before and after there would be a queue that can get overflow. If some of these processes are slow, like you said, it get overflow, right? The overflow will happen on a particular buffer, right? That kind of makes the system stuck. So we'll not see any progress. The latency is going to increase in that case. So basic, whatever you mentioned is correct. But there are in certain systems like Apache Flink, they have some method for controlling this, right? How you can prevent this sort of overflowing of buffer. If they detect overflowing of buffer, what should be done, right? So, but it generally goes with the kind of goes against the philosophy that we are going into, right? We wanted to have more accurate results, but if they happen to see that there is a back pressure, they try to ignore. They try to randomly delete the messages from the buffer, or they will not intake any data, right? Kind of stabilizing the latency, right? But you will see that the Windows process will go down. So we have to see whether any back pressure controlling mechanism has been already implemented, whatever policy they have taken. And that's also a deciding factor for how much would be the throughput here. I mean, sustainable throughput. Here in this case, you can see that the kind of red line would indicate the back pressure, the latency. When there is a back pressure area, it kind of spiked up, but it's kind of going back to the constant number, not much increase. But you can see that there is a significant drops in the number of windows produced by the system, right? So by observing these two, even if they have a back pressure controlling mechanism, we will be able to figure out what is the sustainable throughput of that system on that specific configuration of 2-node and for that particular application of ISP.
The input distribution, like is it a Poisson or whatever? I mean,
nothing as such. So we will just but we could generally say that so right now in most of the experiments or benchmark studies, they kind of keeping the distribution same, or the amount of data within a window same. So it's not skewed or anything when you look at the different real time or real world kind of data. Right. So yeah. So now the question is that because knowing this kind of sustainable throughput is very important to decide which system to use, whether it's Flink or Spark or something else, right? So for most of the modern stream data processing system, we generally opt for systems having high sustainable throughput, which in turn gives a notion that the system is kind of utilizing the resource underneath the resource much effectively. So now, what do we do? I mean, in terms of what all factors we need to consider if you really want to build a system which can exhibit such a property, right? So those were some of the questions that we asked. So if you look at the existing stream data processing system, there are many systems like Apache Spark, Flink, Kafka, Storm, and these are distributed stream data processing systems. And within that category, you can also see that Apache Flink and Spark are major market players. So you also might be knowing about these data artisans and data bricks, right? They have their own cloud solutions even. So they have a pretty good community. And at the same time, we have other systems which are kind of optimized for the specific hardware, maybe the GPU based or CPU based or whatever, something which is optimized for HPC or something which is not scale out, right? So could we categorize this kind of system to see what all things that we have to make sure, to build such a, taking good things from all this category and building a system. So that was our aim. And the first categorization that we did is whether it's a scale up or scale out. Scale up means that it's a single node machine. It's a centralized system where you can increase the the resource. Whereas if it is scale out, it's more distributed in nature. Inter-process communication, inter-node communication has to be established and all that. So some of these categories like Kafka, Spark, Storm, Flink will fall under the category. But the generic norm is that for a single node, it should give good performance, right? But for higher throughput, we may need to distributed setting. We have to go to multiple nodes to intake more data. And then the other classification is one of the primary classification, which is based on the data processing model itself. So we can categorize that into two, and the first one would be the bulk synchronous processing systems, and the other would be the asynchronous stream data processing systems. If you look at the bulk synchronous processing systems, and these are systems also treated as the first generation systems, which are built on top of batch engines. So by this time, you should know, why these batch systems are not so good, right? Tend to give a lot of latencies. So if you are internally using a batch engine, of course, the incoming stream has to be divided into batches, and each batch should be given as input to these batch engines, right? So once you give that as input, so it will generate multiple jobs on top of it and gives out the results, and all the jobs are getting terminated then. Then you will take the next batch, right? So on and so forth. Yeah. Oh, okay. So let's see. I mean, let's go with the same pace and stop whenever it's time. Yeah. So yeah. So this batch system could be also distributed in nature, which means that the batch which is going into the system will be all again divided into multiple partitions, and which will be given to multiple nodes. And internally within these nodes, multiple jobs which get generated, right? So sometimes, and again, after processing the results from each of these batches or partitions has to be brought together for synchronization, right? So sometimes it can be also the case that these jobs that we see there are also dependent. For example, if you have a larger pipeline like multiple maps and filter, etc. So even after all these jobs, multiple jobs, we needed to synchronize these partitions many times. So you can see that there are multiple, levels of synchronization which is happening within the batch and also across the batch. Across the batch is also important because sometimes the window, right, the logical window that you're interested might be residing on multiple such batches, right? So in that case, we may need to further synchronize two batches or multiple batches to get the output corresponding to a window. So there are too many synchronization which can result in increased latency. So that's not a good solution to look at if you're going with the bulk synchronous processing. So the other approach here, the other direction would be the asynchronous stream data processing system, which means that we can now think of having concurrently, continuously running operators, right? They could pass message, and these can be stateful operators, right? So you can take one message at a time and apply some filter and should be able to go through the network and to the final node where you do the window-based aggregation, right? It looks to be the more true stream data processing system in that aspect. It's again not synchronized really with the input batch. So other classification could be based on the generic architecture, whether it's a master client architecture or a pair-to-pair or let's say the client-to-client architecture. So if it is a driver worker architecture or master client architecture, the overhead would be the driver node itself. So generally these kind of driver nodes would maintain the execution plan, and if one worker needs to communicate with other, it has to pass through the driver. So driver can also act as a bottleneck in many cases.
Yes.
Yeah. But we have papers. So some of these are open source. Right? Yeah, in fact, all of these are open source. Yeah. So because we I did my experiments on all these tools, so it's kind of, yeah. And yeah, of course, it's very difficult to go into the code, but of course, you can rely on some of the publications to see the architecture in general. Yeah. So the worker to worker is something different. The task which were previously performed by the driver or the master node has been now distributed to all these workers. So it's more, the better way to solve the problem. So, and again, another classification, what kind of language or programming language that they use for implementing such systems. So you can see that most of the well-known systems like Flink and Spark are built using Scala or Java, which means that they have to run on top of the JVM, and it has serialization, deserialization related issues, and they could not really handle the memory so effectively. So we can't really expect too much from these kind of systems, whereas some applications or some systems are built using C and C++, which has much better memory control, and they can utilize the bandwidth more effectively. So what are the thumb rules that we can use for building such a system? So of course, I should go with the asynchronous stream processing model, right? And then it should be scale out, but should perform good as a scale-up system on a single node. It should then follow the worker-to-worker architecture, and it should be lightweight, go with the low-level implementations on C or C++, etc. So our solution is this system called a.k.a, or Asynchronous Iterative Routing Engine, which we built from scratch using C++ and MPI and pthreads for multi-threading, which can be actually deployed on any system which is pre-installed with an MPI package. So it's a high-level architecture where you can have physical nodes on which you have some Slum-like tool for workload balancing, and then you can install your AIR tool on top of it. So AIR will take a data flow program as input, and will kind of deploy that on the physical node. On the physical node, generally we can have different types of task allocation or result allocation, depending upon the way we want it, whether you want to use the entire node as a single task allocation, or you want to divide that into different task allocations. So Slum generally would give us the flexibility to use in the way we want it. So a little bit more into the different layers here. So like I mentioned, just like any other data flow, AIR would take a data flow program as input. So data flow is a DAG-like structure. And we can also specify the number of data flows here, whether it's 1, 2, or 3, which decides the number of the parallelism. And we have core AIR libraries, which is running on top of physical node, MPI, communication layer, and then workload manager. The core of the AIR would take this input and deploy that many number of MPI processes. So here we mentioned the parallelism as 2, which means that this would be treated as a single MPI processes and deploy that many number of parallel data flows. And if you want to look at the code, you can look at the code. This is how we generally define the data flow, where you will define the operators and establish the connections among these classes. So, yeah. And after the deployment, it would look something like this. You have two processes, as you mentioned that there are two data flows. Generally, in MPI, so it would be assigned rank or process ID sort of thing. It will start from 0 and 1, which help us uniquely identify these two processes, and within which you can have multiple processes or processing threads, which has its own unique identifiers. So how can we generate these unique identifiers? One part you will get from the process ID. The other part you can actually get from the vertex ID, which we give as input. So this combination would give it a unique 16-bit addresses for each of these operators. So, and if you're familiar with MPI, so to establish a communication between two processes or two threads, it should use a unique address, right? 32-bit address. For instance, here, if a filter want to communicate with the reduce operator, they're having a unique ID, 16-bit. They can combine that together and form a message tag, which is again unique, which can be used for establishing a one-to-one communication between filter and reduce. So it's quite easy in this construction to have unique addresses. So another, so we have this 32-bit tags for all the one-to-one communication. And you can see that the beauty of this construction is that each of these processes, if they are aware about the ranks, the number of processes, and the vertex IDs that are given to the other data flow operators, each operators is kind of could easily calculate what address it should use for communicating with any other processes within this container, right? Which is very important. Previously, this kind of address details have been stored in the execution plan and the master. So now we don't need that. Each of the thread is kind of inherently aware. So they can establish a one-to-one communication, which is quite fast. So yeah, so let me know if it is good. Yeah, so again, this is the internal structure. We have multiple threads for listening, processing, and sending threads to increase the parallelism within the operators, right? And at the processing thread level, we define our logic, what logic needs to be applied on a single message. So it would get data from multiple data flows, right? For instance, here the filter is getting something from map and something from the other data flow. So there are two threads which are running in parallel for collecting the data, and then comes the processing thread which will execute the logic, and then after executing the logic, you can push that to the next level. So it will automatically to the respective node, whether it's a reducer operator in the same data flow or the reducer operator in the other data flow. So that's why, so we also have this internal buffering system which kind of creates this producer-consumer pattern. And yeah, so you can also see that each process could actually reroute the messages to any of the subsequent operators within the data flow or across the data flow. So that's why it's called routing, right? It's a routing protocol which is more like a router which takes the data or messages, or like this IP packets doing the routing. So then it could look at the data and apply the logic and route to any other nodes within the system. Yeah, so it's all quite easy. I think I should wind up, and it's very easy to create the data structure. I mean, stateful operators, and the things can be complex, but the air would automatically take care of the thread distribution and all that. Yeah, so this was the interesting thing which we designed. There's a notion called watermarking which kind of keep track of the time. So this will give an idea of whether you have received all the data corresponding to a window, right? So the Google people actually came up with this idea called mill wheel watermarking technique, which gives an idea what time a system should follow such that till that point you have received the entire data, right? So there are not enough time. So it's nothing, it's much about finding out the timestamp, the lowest timestamp, and then updating that as our watermark time. For instance, I'll just conclude with this small example. The idea is that, so if you wanted to, let's say, start our class at 2 o'clock and then doing our attendance. So let's assume that all of you have started at let's say 1:59 or something from your office or from your hostel. So then in the next period you are supposed to be here. So, but if you face some delay in between, right? So so you will reach here at 2:15 or so, right? That's not good. So ideally, if somebody is here is taking care of the time, the wall clock time here, for example, process Sujit, and the person had informed that he has started at 1:59, but stuck up in the middle of a meeting for, let's say, 15 minutes or something. So you can say that I'm having a delay, I'm encountering a delay. So what process Sujit can do, he can turn the clock back to 1:59, right? Which means that we still need to wait 1 more minute for the person to come in, right? So that's the technique here. So we look at the data which is out there in the network and consider the low watermarking time or the low timestamp as our current clock time, so that we will get automatically, synchronous with the way the data is coming into the system, right? So that's the technique. But unfortunately, it's very difficult to implement that in a system with no master node. So we came up with our own technique called hue-meld watermarking, which is again based on the idea that each window will have some meta information which talks about the completeness of the window. So the data will go in. For example, this is the windowed operation. It has a sense of what's really happening, right? Which means that it has only 25% of the data. It has to wait for rest of the data to come into the system, right? So it's like implanting some completeness information into the message that will give a sense of the time. It will also work for the arbitrary setting. Yeah, just flying out. We got good experimental results. It's been observed that in a single node setup, we could actually do 7.6 gigabytes of data processing per second. But when we try to increase that to a distributed setting with our own configurations, you can see that per second, we will be able to process 42 gigabytes of data for using just 8 nodes. And when we tried that with 16 nodes, it went up to 60 gigabytes per second. Just come to be the state of the art now. And summarize, it's a good compromise. We kind of proposed a simple, small like this Occam racer. We're proposing a simple design which turned out to be the right one for stream data processing system. It's an open source system. You can go and download and try it out. Yeah, these are some of the publications. Yeah, so we have also some extension. The people are working on it to extend this to do, more machine learning sort of thing in parallel. Mostly in the terms of data parallelism. We could even train. Some of these operators could be a machine learning operator, where we could do training in parallel. My colleagues at University of Luxembourg, and there is also planning for a much more generic system called a stream span, where each of the events, which we consider are point events, but it could be also a generic class where it comes with an interval. Okay. And some of my students also working on the reasoning aspect, how we can do distributed reasoning on this kind of system. Okay, thanks a lot. Yeah.
Let's thank the speaker again, and
Thank you.
and thank you all for attending. Thank you.